And today's speaker is Professor Nasir Ganikhodjaev from Mathematical Institute of Uzbekistan Academy of Science with the talk Lattice Models on Kelly tree with Competent Interactions. Please.
Okay, thank you. Good evening. Thank you very much for this possibility to present some results. So, title already informed. Lattice models on Kelly tree with competent interactions. So here, first of all, a little bit introduction, later history, this outline, which one I will follow this presentation. So the most fundamental problem in the theory of phase transition or equilibrium statistical mechanics certainly that of giving description of limit Gibbs distribution. That is some type of probabilities. The limit Gibbs distribution for Hamiltonian H are constructed as infinite volume limits of conditional Gibbs distributions, infinite volumes with different boundary conditions. Here we have some difference from usual stochastic processes because they were considering finite dimensional distribution, and after this try to construct distribution on whole space. Here we consider conditional Gibbs distribution. After this, try to find limit. And of course, this limit will depend from some boundary configuration. I will say a little bit later. So in the usual formulation of this problem, we consider one parameter family beta H of Hamiltonians, where H is Hamiltonian and beta is value 1 over kBt. Here inverse temperature. Here kb is a Boltzmann constant, and H is given Hamiltonian. It is extremely hard to give complete description of limit Gibbs distribution for arbitrary Hamiltonian. So only for some one-dimensional models are given complete description of limit Gibbs distributions. And this problem practically was solved by Gibbs himself, Ising himself. One of such models is 1D Ising model, which one I will discuss later. Now, first of all, some definition and Ising model. And so the Ising model is a mathematical model of ferromagnetism in statistical mechanics. The model consists of discrete variables that represent magnetic dipole moments of atomic spins that can be in one of two states, +1 or -1, or spin up and spin down. The spins are arranged in a graph, usually lattice, allowing each spin to interact with its nearest neighbors. So simplest model when we consider only interaction of nearest neighbors. This model was invented by Wilhelm Lenz in 1920. It is named after Ernst Ising, a student of Lenz who chose the model as the subject of his doctoral dissertation in 1925. He tried to explain, using this model, certain empirically observed facts about ferromagnetic materials. So, for example, it was known that in a very low temperature, for metal has obtained some magnetic properties. So now we consider some infinite countable graph. So V is a set of vertices and L is a set of edges. So V is countable set. So now to vertices X and Y we will call nearest neighbors. If there is X, there exists a H connecting them. And usually such nearest neighbor we will denote like this way. So now, of course, we can consider different countable graphs. ZD, for example, this is one examples countable graph, or more convenient for exit solution, Kelly tree. That is, Kelly tree is of order K is a graph without cycles with exactly K plus edges issuing from each vertex. So this here picture, I consider semi-infinite Kelly tree of second order. That is x0. This is root of this tree, and you can see. So this is from each vertex except vertex root. We have three edges. Uh, so advantage of models on trees, where we don't have cycles, is that no approximation have to be made, and the calculation can be carried out with high accuracy. The important point is that the statistical mechanics on trees involve non-linear recursion equations and are naturally connected to the rich world of dynamical systems. This one is presently under intense investigation. So later I will consider a graph on Z plus. This is interesting graph because this one is one-dimensional integer lattice, and from another side, this is semi-infinite Kelly tree of first order. That is, we can consider Z plus as integer lattice and at the same time as Kelly tree of first order. This is very convenient for future. So we have vertex, this is beginning vertex 0, and all other vertex has edges, no cycles. Okay, so now I will consider first of all models on Kelly tree. Maybe in the last part, formulate some problem for ZD. So we define a configuration of Ising model as function. And denote the set of all configuration by omega. For each subset, finite subset, we let this configuration of this set, and omega W, this is the set of all configuration on W, and sigma itself is the set of all configuration on V. So now what is Hamiltonian? Hamiltonian of the Ising model is defined as the following sum. So here G1 is constant, specifying the interaction of the neighbors, spins, neighbors of spin at spins at the neighbors X and Y. So we consider this infinite sum. Of course, this is so we cannot use in such form. So here we consider only interaction nearest neighbors. It is the simplest model. So for G1 positive, exists some limit Gibbs measure, which one is called ferromagnetic phase. And if G1 negative, also exists limit Gibbs distribution, which one is called anti-ferromagnetic phase. So that is, for this model, we have only one phase. If G1 positive, ferromagnetic phase, and if G1 negative, which one is called anti-ferromagnetic phase. That is phase diagram here, very simple. So now, if we will consider except interaction of nearest neighbors, also interaction of some non-nearest neighbors, spins such model we will call as model with competing interactions. That is, we have two or more interactions. So here now very important form of this neighbors of another type. So first of all, we will say, so two vertices, we will call second nearest neighbors, or in some literature, next nearest neighbors, if distance equal to 2. Distance here is computed as the number of the edges connecting these two vertices. And we can consider two types of second nearest neighbors. First type, if both x and y belong to the same branch of our tree. So such nearest we will call prolonged. So for example, this vertex and this one, they belong to the same branch. And second type, if they are distance for these two vertex also 2, because we have two edges, but these two vertices also belong lies on the same level. So for this reason, I will call this as one level with second neighbors. So, and phase diagram of future models will essentially depend of which type second nearest neighbor we're considering. So we have two types, prolonged. If they both belong to the same branch, in opposite case, this we will call as one level second nearest neighbors, and denote like this one. And here, very important, the existence of competing interactions lies at the heart of variety of original phenomena in magnetic systems, ranging from the spin glass transition found in many disordered materials to the modulated phases with an infinite number of commensurate regions that are observed in certain models with periodic interactions. So Ising model with competing interaction has recently to be considered extensively because it has a lot of applications. So appearance non-trivial magnetic orderings. And if competing interactions are defined for prolonged second neighbors or prolonged third nearest neighbor, which I will consider later, that is, we consider spins belonging to the same branch, then corresponding phase diagram is very rich. I will show this later. And if second or third neighbors belong to different branches, in this case, phase diagram consists of only four, no more than four different phases, namely maybe paramagnetic, ferromagnetic, paramodulated, and phase with period 2, so which was called anti-ferromagnetic phase. So let us consider examples. So this is here for this model, we consider interaction of nearest neighbors and interaction of one level second neighbors. For such model, we are producing some recurrent equations. Only for last model, simple model, I will show how we are producing such recurrent equation. Here, let me only show phase diagram. So this that is interaction of nearest neighbors and interaction of one level second neighbors. Then a phase diagram has, as I mentioned above, like this one. That is, we have three type of phases: ferromagnetic, paramagnetic. This is magnetization 0, and this anti-ferromagnetic is period 2. That is here rather simple, yes, phase diagram. Three different phases. But if we will consider this model was considered by Benimenius 1981, here interaction of prolonged second neighbors and the same interaction of nearest neighbors. This case phase diagram very rich. So you can see here consists of a lot of, here a very important part arise modulated phases. Modulated that is maybe with very high period or aperiodic also. So it's independent of our recurrent equations. And this antiphase, this is the phase with period 4. So we have, you can see, so essentially different than this phase diagram, more richer than previous one. And this one image model also one can consider as counterpart of axial next neighbor Ising model defined on a regular lattice because first of all was considered such models on ZD and there was proved to exist arise modulated phases. Later one image shows so this was the same property we have for Kelly tree. So now later these three others consider combined interaction of prolonged second neighbors. Is here one level second neighbors, and this one is nearest neighbors. That is now we have three parameters, G1, G2, G3. So now phase diagram now will depend from, no, for example, in our case, is from ratio G1 to G1, G3 to G1. So maybe here this axis, horizontal axis, this is minus G2, G1. Vertical axis, this is T over G1. So for each point, we can compute T, G1 over T and G2 over 2T. And for fixed this ratio, also we can compute G3 over 2T. And after this, to investigate corresponding phase diagram for this fixed point. So now here give different phase diagram for different ratio of parameters G3 and G1. For this case, we have such phase diagram. For this case, a little bit differ, but the same, practically the same phases, but maybe in a little bit different form. So here we have ferromagnetic, paramagnetic, modulated, two-phase, anti-ferromagnetic. So a lot of different phases. So in this case, so only maybe change it on the shape of this phases, but the same, practically the same phases. We have the same phases. Later, these two others considered model for complete interaction first, second, and third nearest neighbors. First, this is our nearest neighbors. Second, this one here, prolonged second neighbors. And third nearest neighbors, this is also prolonged third neighbors. That is neighbors with distance 3. So this Hamiltonian consists of these three summands. So for this case, also if we assume so G2 0, that is this ratio 0, we have such phase diagram. And here has a new phase, this is 3 phase with period 6. This has some physical means. This one P3, this exactly diagram phase with period 3. This is phase with period 2, is modulated, maybe any period, ferromagnetic, and so on. So you can see, so this essentially differs than previous case. And here again, for different ratios G2 and G1, we produce different phase diagrams. But here practically the same phases, maybe on the size, a little bit differ. So here novelty arise also phase 2, phase 3, period 3, period 2, modulated, so a lot of phases. This is for case with this ratio 0.5. So this is for this case. So later we consider model where we consider interaction of here nearest neighbors and the interaction of certain neighbors, but when the certain neighbors belong to different branches. One of them I denote as L, one of them R, because, for example, model for certain neighbors, this is two neighbors, two vertices, this is certain neighbors, but this is left because vertex from left lower than vertex from right. This is left, these two vertices, they are right, that is for another reason. So considering such models, here again we have three parameters. So differences, if previous others considered only interaction prolonged neighbors, they were considered interaction of two-level third neighbors. Here we have interesting phase diagram. So here ferromagnetic phase, anti-ferromagnetic phase, paramagnetic. Is this PM paramagnetic modulated? This period 2. This is here also this new phase. It's magnetization 0, but here we have period 2. And here again, this phase depends from ratio GR to GL. This is GR interaction of third neighbors type of R and the respective L. And for such ratio, when they are equal, we have such phase diagram. When the ratio -1, we have very interesting such phase diagram. So now I'll stop in more details one-dimensional Ising model. So here I can conclude this part as phase diagram essentially depend from type of second or third neighbors. For prolonged second or third neighbors, we have very rich phase diagram. For one level or two level, rather pure, not so much. 4 or maximum 4. So now let us stop for one-dimensional Ising model. This is so here consider. I will show how in general case we can produce the recurrent equations. So lambda n this fixed subset, sigma n the set of all configurations, and this one is a fixed boundary configuration for complement of lambda n by fixing some configuration, and this is called boundary configuration. Then we can consider conditional Hamiltonian, that is by fixing boundary configuration, and compute Hamiltonian for configuration on lambda n. This is already finite sum here. This is interaction of inner spins here and here. This is interaction inner spins with boundary. We have such sum. So now this is computed. We can compute because this is finite sum. So now we can define conditional Gibbs measure on this finite subset lambda n with fixed boundary configuration. This one is following measure. So this ratio beta, this is inverse temperature, and this is partition function. This is sum of such type. That is, we will have a conditional Gibbs measure. So now this set of all configuration on lambda n, sigma n, we can split on 4 different subsets. This each of them is two-dimensional cylinder sets. It is here we fixing value spins at 0 and side 0 and 1. Here 1, 1, 1 minus 1, minus 1 plus 1. That is, we have 4 possibilities. So now respectively, I can split partition function also for summas. That is, here we consider summation only for configuration from this part, here from this part, this part. Of course, there are some equal to our previous partition function. So now, in this case, this conditional gives measure. I can substitute and compute like this ratio. So for brevity, I will introduce new variables. And for let A, this exponent beta g1, and B, exponent beta g2. This is parameters which will depend from temperature and interaction, spin interaction parameter. So in high temperature, when our matter will be like gas, we have the paramagnetic phase. And in this case, for very high temperature, we will have such equality asymptotically. Z1 equal to Z4 and Z2 equal to Z3. So that is, we can introduce now, renormalize our previous values like this one. So now this XX, Y1, Y2, there will be already finite something. So we can investigate the limit behavior. So now replacing from here, we can find express Z1, Z2, Z1 from X, Y1, X, Y1, Y2, and pass two new variables. And this previous our conditional Gibbs measure will be equal to this ratio. And when n go to infinity, if such limit exists, we will show so such limit exists. The limiting Gibbs measure of this one-dimensional cylinder set will be equal to this limit of this ratio. So here, of course, if such limit exists. So now we can produce recursive equation, this Z1 n plus 1, this is the same partition functions, part of partition function on lambda, which one consists of from 0 to n plus 1. So fixing 0 and side 1, we can produce such equations. That is Z1 equal to this one, and so on. So now from these equations, coming back to X, variables X, Y1, Y2, we have this ratio. So now we can, we have these recurrent equations. Now we can consider what we'll have when n go to infinity. So here, note, so the average magnetization of n's generation is computed as expectation of this rendered variable. Substituting, we have this ratio. That is, magnetization will be equal to 0 if y1, y2, both of them 0. So now we will investigate the recurrent equations, starting from random initial conditions for y1 and y2. We can iterate these previous recurrent equations, relations, and observe their behavior after a large number of iterations.
Excuse me, am I right
Yes.
that you choose am I right that you choose in random initial condition just to investigate the variety of possible limits?
Yeah.
So you don't have actually a general picture what will happen in the limit. You want to just to get feeling what it can be. Yes.
No. Practically, I can compute y1, y2 from definition. But
Mhm.
this is, but we can choose and arbitrary to also result will be the same.
Mhm.
So now, if we will investigate behavior of these three
Mhm.
values for n going to infinity, so here may be different cases. Maybe so simple situation when we reach fixed point.
Mhm.
That is, this fixed point exists fixed point for all three. So now, if we have and this existing of fixed point, of course, will be depend from parameter A and B. That is
Yes.
will depend from temperature and value of G1, G2.
Mhm.
If we reach fixed point, and if the y1, y2 equals 0, this means we will have in the limit we will have paramagnetic phase because magnetization will be 0. And if y1 or y2 they are different than 0, then this phase is exactly will be ferromagnetic phase.
Mhm.
And in the case of paramagnetic phase, in this case, this limit exists and equal to 1 over 2. That in this case, our paramagnetic phase coincide with uniform distribution on that set of all configurations.
Mhm.
In the case of ferromagnetic phase, this limit differs than 1 over 2. And we can produce such phase diagram. Mean of this phase diagram is, again, this axis. This is exactly gamma. This is minus J2 over J1, this axis. This axis T over G1, this alpha. So if I will choose arbitrary point on this square, for example, in this case, I can compute a parameter A and B, and using this parameter, iterate previous our equation, and to investigate what type limit we will have. For example, for any point from here, we will reach, we will have paramagnetic phase. That is, exist all three limits, and limit for y1 and y2, 0. Limit for x, something different, positive number. And the same I will have for any point for this part of square. And here we will have modulated phase. That is, we will limit does not exist, but we will have cycle of highest order, or maybe aperiodic. So we'll consider limit. That is modulated. That is this yellow, this anti-ferromagnetic phase. This part is ferromagnetic phase. That is, we have practically for one-dimensional case also we reach modulated phases. This is very interesting part, strange, because usually one-dimensional case very we can think that is very simple case. So for complete interaction, we reach here also modulated phase. So now, for usual Ising model, one-dimensional Ising model, Ising himself proved. So for any fixed boundary configuration passing to limit, we will have the same single limit, limiting Gibbs measure. That is, limit does not depend from choice of boundary configuration. This fact was proved by Ising himself for usual 1D Ising model. But when we will consider complete interaction, we can reach phase transition. That is, we can show so there are at least two types of boundary configurations. If passing to limit for one, we will have two different limit Gibbs measures. So, no, first of all, This one already was shown. So limit Gibbs measure equal to zero. So, and for another one-dimensional cylinder set, we have such limit measure, and their sum equal to one, of course. And for limit Gibbs measure, we have these two equalities. So now let us consider, here I am considering ferromagnetic phase. That is exists limit, y1, y2 non-zero. So we have fixed point. Here it's y1, y2. This is the limit value non-zero. Now from this, considering a ratio of these two equations, dividing this equation to second one, we have yeah, here, yes, have such a ratio. So introducing new variables, this ratio y1, y2 is t. We come to simple for fixed, for in the limit, we're coming to simple quadratic equation. And for this quadratic equation, there exist two real roots if discriminant satisfied to the condition. Discriminant greater zero if we have this inequality. So now replacing A and B by they are because A this is exponent beta g1, B this exponent beta g2. So passing to these variables, gamma and alpha, we have this equality. I can rewrite like this one. And to graphically we can verify. So this equality is valid for this solution of this inequality contained our domain of ferromagnetic phase. That is on ferromagnetic phase. Here, for example, here, my previous inequality is valid. That is, there are two roots. And from this one follow. So now we can also verify numerically. So we have two measures, mu plus generated by positive boundary configurations, and mu minus generated by a negative boundary configuration. That is, we have phase transition. So now here, so as conclusion, I can say for 1D Ising model, first of all, with complete interaction, phase diagram contain modulated phase, and also here we can have phase transition. That is, for different boundary configuration, we can reach different limit Gibbs measure. So now coming back to Z2. So from previous, you can see, so one can expect that the model with competing interaction on K3 has enough similarities with model on periodical lattices ZD. So for example, in both cases, for the same model, we have modulated phase, existing of modulated phase. So moreover, a detailed study of its properties can be carried out with essentially. So that is for K3, we can find exit solution solving the recurrent equations. For ZD, we cannot this one. We can only approximate or can only estimate some value of pair is we have modulated phases and some and other phases. So on Z2, for this previous model with competing interactions, this one define it more exactly. So here we have interaction of nearest neighbors and second neighbors. This one being restricted to spin belonging axis that parallel to axis OY. So now, no good picture. This is Z2. That is the nearest neighbor. This is all vertices connected with one side of this square. This nearest neighbor for this one. But as second prolonged second neighbors, in this models was considered only interaction of second neighbors belonging to lying on this line. That is, this one is prolonged like second neighbors, or this one. The other did not consider a situation when as second neighbor does not consider neighbors of such type. It is only vertical. So now, what will be if we will consider interaction of second neighbors, but which one is form angle? That these two neighbors, vertices, they are also second neighbors, but they are belong to different lines. This is vertical one lines, this is horizontal lines. That is my not question, my problem. So to show, so in this case also, if we, as second neighbors, we will consider neighbors of such type. That is, in this case, I think also we will. Its phase diagram does not contain. So we can expect. So its phase diagram does not contain modulated phases. That is, and this is a result maybe also we connected with random fields. Maybe here also will be some connection with depend of type or form of competing second or third neighbors. That is all from me. So thank you very much for your attention, and if any questions.
Thank you very much. Maybe somebody have questions or comments, please. I have several questions.
Yeah.
As far as I understand, you use the same methodology of this recurrent equations for paths for this statistical sums when domain is growing to infinity. But now it looks like you have a lot of statistical sums depending on the boundary conditions, because when you use this, when you study this Z2 case, the domain has a very large boundary, so you have a variety of boundary conditions.
Yes, on Z2 we cannot use this, we cannot produce recurrent equations because for three, so here there are some another methods, so some so-called contour methods or something else. But for Kelly really for some, because what does mean this each of these results phase diagram, that is we can find for example, for some boundary configuration, we will have paramagnetic phase, but they are, as if I will consider this limit Gibbs measure, they will have maybe different value for different for the same one-dimensional or two-dimensional another cylinder sets. But here magnetization 0. Here already magnetization non-zero. So here, of course, I have computed fixing, but we can show this is so for some boundary configuration we will reach such type result. For another boundary configuration, another phase diagram, and the number. So, for example, for one-dimensional case, uh, uh, existing of fields, for example, here for one-dimensional case, it does not depend from choice of for any boundary configuration, we'll have the same result. Only here for positive boundary configuration, we have one limit Gibbs measure. For negative, another Gibbs measure. It is only here I have phase diagram, phase transition. For usual Ising model, already I mentioned, we have only single type of phase, that is maybe ferromagnetic or paramagnetic. And there, for one-dimensional case, result does not depend from choice of boundary configuration. But we have interesting different cases. If for chemistry of higher order, 2 and more, or for that d with d greater than 1.
For
That is,
chemistry, you also just take special boundary condition and then consider recurrent equation.
yeah.
Okay. Okay. Thank you. And as far as I understood, this Kelly tree was chosen due to some special, how to say, ordered structure. So maybe you can consider not only Kelly tree but a graph which is realization of some random tree like Ryoshani.
Yeah. So, there are a lot of now some investigation for random trees, for or maybe so-called Bryatid tree. So when from one vertex issue arise p edges, from neighbor q. That is, we have different type. But here for regular trees, only in this case we can produce, but rather simple way, recurrent recursive equations. Because maybe let me show here. Okay, here we are. So okay, this is, we can consider path here, and after this pass to this path.
Yes,
In this
yes,
case,
I
this
understand.
part divided in the two similar already subgraphs. That is easy to produce
But
recurrent
I
equation.
think that if you substitute the Scaly tree by the random coalescence process, for example, Pitman coalescence, then you will know everything about the distribution of number of vertices and edges on any level. And I think that you can produce the stochastic version of your recurrent equations. And maybe it can be interesting and solvable.
Yes, interesting suggestion. Yes, of course, but no, at present I know what is this path.
Okay, I see. Uh, okay, thank you very much again.
Okay, thank
Uh,
you.
and this is the end of our session for today. And let me announce that next time, next week, we will have Korokhod readings. We will see talks of our young colleagues. Uh, I think this time all of them will be from Kiev initially, at least. So we will start at 4 p.m. in Kiev time, not 5. Please please carefully look for announcement. Okay, thanks again, and see you next week. Bye.
Okay, bye.
Thank you. Bye.
Goodbye.
Thank you. Bye.
Bye.